All right, well, I'll get started. Thank you, everybody, for joining SEI Philadelphia for another technical webinar. Looking forward to this one, as always. It's concrete service life modeling on the Nottoway Bridge case study. It was in Virginia. So before we get into the meeting, as always, a couple housekeeping items. This meeting is being recorded for that we can use for if you miss anything. It'll be on our YouTube page and it'll be linked on our website. So if you miss something or need to go back, you can always check it out. This is a town hall, so your microphone and camera will be has been disabled. So there is a Q&A function in this meeting. So if you have any questions, feel free to use the Q&A function. If you have, feel free to ask a question during the presentation, so because it's fresh on your mind, and at the end we will we'll get to all your questions. As for SEI Philly, the website's right there, and if you have any questions, comments, concerns, you can always email us at phillysei@gmail.com. And a lot of our information is on LinkedIn, so grab your phone, grab a picture of the QR code there, and I'll take you to our LinkedIn page, and you can follow us on there. This is this year's board members. We introduced everybody last time, but I'm Mike Urban. I am your chair, and on your screen, you'll see the rest of the board there. Colin, Greg, Alex. I don't think Nathan's on just yet, and then Justin and Kylie, and our past chair is Keith. So we're constantly working hard to get you guys some good content. As always, thanks to our sponsors from last year for the SEI golf outing. It was a great success. We were able to raise a lot of money for scholarships for the students in the area schools. So it's always great to be able to help out the younger kids and ultimately our future coworkers. So again, please come out. We are looking for the next event, the next golf outing in May of next year. So come on out, and if you can sponsor, we would appreciate that just as much. For our upcoming events, we do have another virtual event coming up on November 18th next month. We are finalizing the details, so please be on the lookout for that. It'll be coming out soon. We will be skipping December since it's usually a very busy month for everybody. So enjoy your holiday break, and then we'll get right back into the thick of things next year. Starting in January, we'll have another technical session. We will have our in-person joint meeting with DVGI, ironing out the details. So again, look for that as well. It'll be a great presentation, and it'll be good to be in person and seeing everybody out. We had a good fall social, so it looks like we're going to do it again. And so in February, we're looking to have a winter social, so be on the lookout for that. And then in the winter, we will be doing our SEI college event. So again, look for that information, and we may be, we'd always welcome, our members here to come out, support the chapter, as well as support the kids and offer anything. So we will be looking for that. Look for that information coming up soon. And then, as always, you can see some TB determines in there. We're always looking for projects for you to present. So if you have any projects you'd like to present or talk about, reach out to us, and we can see if we can get you on the schedule. As I mentioned, we did have our fall social at the Workhorse Brewing. It was a great time. It was good food. There was the murder mystery trivia. I think we did all right, maybe 5th or 6th place. I can't remember, but it was a good time. It was great to see everybody. We had some students out there, as long as some professionals. So it was good conversations. And like I said, look out for our winter one. We can do it all over again. So moving on to today's presentation, we have a great speaker. We got Travis Green. He is a principal at WGE in Washington, D.C. He has 25 years experience with his focus on assessment and repair of existing structures. So what you hear about today. He specializes in welding, non-destructive testing, precast concrete, and the post-tension concrete. He's a current chair of AWS D1.1 committee, and he's also a member of other committees in AWS as well as PCI. So it's great having Travis here, and I'm looking forward to his presentation. So this time I'm going to stop sharing, and I will hand it over to you, Travis.
Thanks, Michael. Appreciate that.
Let me get you here.
You good there? Let's see.
I think we got it.
All right, you guys see that? All right, perfect. So this is going to go into some service life modeling basics, and then we're going to relate it to a particular bridge, right? This Nottoway Bridge down in Virginia. It's down near Richmond. I thought it was a neat bridge just because it's built on top of a dam, so that's what you see there on the screen. So kind of just an interesting structure. So I'll give a little intro on WJE and myself, or I've already really gotten myself, service life modeling basics, the structure, what we did, and then outcomes, and then an open discussion. So who is with Janney? So WJE is our initials. We're about 850 people, and we specialize in assessment and repair of existing structures. So we're really not designers, right? We're not designing new structures like many potentially on this call. In particular, we have a bunch of laboratory capabilities, NDE capabilities, load testing, instrumentation type work. So we're a little bit different than the standard kind of inspection firm or like building design type firm. Some of the structures that we've worked on here, right top left, is Champlain Towers. We're one of the primary researchers on the failure analysis, and you may have seen Matt Fadden's presentations on that. Middle top is the National Cathedral in DC. Top right is the assessment of some of the stainless steel on the St. Louis Arch. Bottom left is dated now, but obviously that's 35W. We were the prime investigator for that with MnDOT. And then middle is the Washington Monument, and I think right is the Pittsburgh Bridge that had the fire underneath it. About me, again, 25 years, all at WJE. I wanted to bring up the photos on the right. So this is the nearest I've worked to you guys up in Philly. So this is the Commodore Barry Bridge. I think Jen Lanning gave this presentation previously, maybe last month. And so I just wanted to show you a few of the kind of cool, what I think are cool, probably nerdy. These are slices on this image from the Commodore Barry Bridge cores that we extracted, and then what they're polished and etched, and they're showing indications there. So just kind of a follow up to what Jen talked about last time. I thought these were nice images for you guys. So what is service life modeling, right? Well, why would we do it, right? We're really trying to make good decisions about existing structures, trying to figure out, right, how much chlorides do we have? How much concrete carbonation do we have? Can we extend the life in certain ways? Does this material need to be removed and replaced? This talk will focus on existing structures, but this methodology can be applied to new structures as well. So what are the basics, right? So really it's about, and I'm going to talk mostly in terms of chloride infiltration, right? Because that's what drives most of the concrete related, corrosion related damage in concrete structures in this area, right? So we have basically chloride diffusion. We apply chlorides to the surface in general, right? They diffuse through the concrete. You end up at some point you get to a corrosion threshold, right? The concentration of the chlorides is so high that you initiate corrosion at the surface of the bar. And then as that corrosion occurs, right, you start to develop damage, and eventually that damage can be seen on the screen. And Michael, can you see my pointer when I move it?
Yes.
Or no? Okay. So again, we have this initiation time where we're building up chlorides, right? We start to have corrosion, and then that corrosion progresses, right? until we eventually can see it. So there are several different reference standards out there, EN 1990, ACI 365, and some others. We developed an in-house program which we call CASEL, Corrosion Assessment and Service Life Evaluation, and we've used it to look at numerous different types of structures. You see hyperbolic cooling towers on the right. You see these wharfs from down in Houston, bridge deck, and then we worked on a NASA building that was having a bunch of challenges too. So that service life modeling, you can do deterministic modeling, which is kind of the ACI 365 method. We generally do probabilistic modeling, and I'll explain what that means in a minute. And again, new and existing structures. So what are we really doing here? And don't worry about if you haven't seen fixed law in a long time, probably I don't look at it very often either. What this slide really says is we're going to take a solution, we're going to put it on the surface, and it's going to diffuse, right? So that's a diffusion coefficient. So over time, the chloride concentration changes with time, and that is based on a diffusion coefficient through the concrete. That's like a material property, right? So over time, that chloride penetrates deeper, and so we're estimating that, and we're quantifying that in ways, right? So what we're going to talk about today, there's a couple different ways to handle this. But what we're going to talk about today is this, what we call a finite difference model. There's analytical models, which really get into like both the depth and where it is on the structure. We're going to talk about basically we're not going to talk about spatial, like meaning X, Y coordinate type stuff. So just a graphic to show you what happens, right? So this is an example of the finite difference method, right? So we start off, early, and we apply chlorides, right? But nothing else through the depth has chlorides in it, right? But over time, those chlorides, they diffuse by Fick's law. And as you get farther and farther along, right? This horizontal is the concrete surface, time is to the right, depth is down. So those chlorides diffuse down, right? And we get more and more chlorides down through. And at some point down here, right, our bars are going to sit there, yeah? So at some point, right, we're going to start to see chlorides at the bar level, and that's going to potentially result in corrosion if we exceed, these kind of threshold levels. So this graphic shows, kind of interactively, right, that we're increasing chlorides, right, at the surface. And then when they start to diffuse, and they get more and more and more as they get deeper into the concrete, and eventually, right, if we have a bar at 1.5 inches, right, we have chlorides over a threshold, which we would say start the corrosion process at that bar, right? That bar is no longer passivated, right? So just another kind of graphic there. And so what we do is we say, listen, we're going to go get a bunch of cover information. We're going to do testing to get the diffusion coefficients of the concrete, right? And these are to basically result in some kind of distribution curve. We get exposure information, how much chlorides are available, basically, right? What is the surface chlorides that we have? And then there's several different chloride thresholds depending on bars. For example, stainless bars have a very high corrosion threshold, right? Black bars have a much lower corrosion threshold. We get all that information, right? We do some Monte Carlo simulations, and we end up with a curve like you see here, right? So we are in this curve, right? We're saying ultimately, hey, we're going to see damage, if we're here, we're going to see damage at 20% of this surface, right? At 75 years, right? So we're trying, and this damage areas, right? That's basically spalling, essentially. And a lot of agencies use, somewhere between 15 and 40% surface area as a trigger for some kind of repair work or removal and replacement work. I think this slide provides a little more visual kind of input to this Monte Carlo normal distribution kind of stuff, right? So we get a bunch of cover. This is a plan, so consider each one of these little boxes a plan, right? and we get a bunch of different covers, right? And then we have a bunch of different exposures, right? How much chlorides are available to us. And then we consider, right, what the corrosion, the diffusion rates are in a bunch of different areas, right? There's Nate's coming on. Right. And then generally we have chloride thresholds that are constant, but in this particular example we have different corrosion or chloride thresholds. And so ultimately what we do there is we try to predict the initiation time, right? So like in theory, you could have a bunch of different corrosion initiation times depending on all these variables, right? So to kind of to go back to that point, you could have, for example, low cover, right? High diffusion, high exposure, low chloride threshold, and you end up with a curve, right? That's very steep. Does that make sense? And so, and then if you look at another set of parameters, and that's how we build these curves. So this is a XY, kind of a plan type, explanation of that. So how do we do that, right? So we go and get physical data, usually with GPR, and it's verified via openings, and we curve fit the concrete cover data, right? And that's not always a normal fit. That can be a log normal fit of the cover data, and so we use that as part of the Monte Carlo simulations. We then we like cores. Some people like powder samples. I think West Janney's opinion is generally that the powder samples can cross contaminate, and then so we do these slices of these cores, and we use those. We do acid soluble chloride testing, and then we curve fit chloride profiles to back calculate surface exposure, right, and diffusion coefficient. So that's how we get that data. Then there's also like the average temperature matters. Surface chlorides obviously are like I said, are back calculated. When it gets its first exposure, the corrosion's not going to start until the chlorides get to your bars, right? Generally. So, if you don't put it on for the first 10 years, you're not going to have to worry about that for the first 10 years. And so then this buildup time is how long it takes for you to get to the point where you exceed the corrosion threshold. The corrosion threshold, so on the right-hand side, we have just kind of changed. We wrote a paper on this in 2021 about some of the parameters that we use for uncoated and epoxy bars and galvanized bars. So I don't worry too much about the individual numbers. I just know that this is a component of this calculation. I think just as a side note, I know this sounds a little kind of statistically based, which it is. This is all kind of been formulated, and we can actually do this pretty economically at this point for like one particular location and one run. It's not actually that much time. But we have chloride thresholds that we use. So that's how we get to a kind of a damage plot, right? And I'll show you a damage plot for Nottoway in a minute. So this is the bridge, right? This is a little bitty bridge out in the middle of nowhere. It holds a reservoir. The dam below is part of the Army Corps. The road is VDOT, so it complicates things a bit. This is just where it's at and kind of what it looks like, right? Kind of zooming in from left to right. We were retained by KCI Technology, so we were kind of complementary to this potential design team. And so we were responsible for rehabilitation evaluation. So the idea was, did they need to cut this bridge off this dam and move it downstream or upstream? They couldn't really move it upstream, but downstream. Or could they renovate it, right? So this is just some plans. It was built in 1942. Just some elevations here. So built in 42, they put new deck on it in 70. They'd done some more work in 90, and then they'd had several different versions of these assessments. And recently in 2023, the superstructure went down to 3. That's because of a bunch of corrosion on the steel girders. So what did we do as part of the KCI team? So we did a visual inspection, just like pretty much anybody else would, right? We saw a bunch of deterioration, documented that. We mechanically sounded the deck, right? Certain areas of the decks, definitely had some challenges up to, 20%, distress within a particular area. Again, this is chain drag type stuff. This is not the automated sounding type work that some others are doing, because it was several years ago. We did ground penetrating radar work to look at cover. So obviously this particular item, this feeds right into the service life model, right? Because we need to know where the bars are to get some kind of normal distribution curve on reinforcing steel position. And so this is what that it was intended to do. We then came through and did some half cell potential measurement. So this is measuring whether there's a high likelihood of ongoing corrosion, right? So, generally speaking, the more negative you are, generally, the more likely there is for corrosion to be there. It's literally, if you guys haven't seen it, it's a voltmeter and like a copper sulfate reference probe. So you see me here, frankly, a long time ago with a voltmeter and a little probe. They're connected, right? One lead goes to an attachment onto the rebar, and the other, this little like sponge with the reference anode, gets moved around, right? And you can see the little dots from the water on this pier at Nottoway, right? And so then we're plotting these to show whether we think that there's ongoing corrosion, right? Doesn't show the rate, doesn't show corrosion rate, but it gives you an indication of whether there is ongoing corrosion. Also, just as a warning, I like this technique, just a warning, if you have galvanic anodes, if you have spray applied zinc, if you have kind of an impressed current system, this technique won't really work as well, right? So it's meant, also if you have epoxy coated bar, the technique might not work at all. But in this structure, it had black bar, and we felt pretty comfortable with it. So we also did linear polarization testing. So this uses the same connection as the half cell potential measurements, but it's really trying to back out how fast the steel's corroding, right? And I won't get into the specifics because I don't know that this group really needs or wants that at this time. But what we're trying to figure out is how fast is it corroding. So we may know that it's corroding. Now we want to know how fast it is corroding. On this particular structure, the corrosion rates are actually quite low. Some of that might be due to it was dry in that period, that time we were doing measurements. That does have an impact, and that at the time it was really cold, and so that also can affect these measurements. Michael, are you checking the Q&A? Do we have any in there right now yet?
Nothing right now.
Okay, cool. All right, we also did electrical resistivity measurements. This is concrete. This is a property. This is measuring a property of the concrete. So it's tendency to impede current flow, right? So if it's low, right? If we have low resistivity, right? We generally have low chloride diffusion, right? That or corrosion risk, I guess is a better way to put it. So in this particular structure, we got low values. I will say, I think it was so cold when we did this testing that I suspect if we went back out there in the summer, we would get different numbers, even if they were not, I don't know that they would be as low as we got, but I think they'd be low, right? Right, and you can see here, right, we're getting, from a kilo ohms perspective, we're getting in the 200s, right? So we're well in the low category here of corrosion risk, right? So materials testing, right? So we do acids. In this case, we did acid soluble chlorides. This is an image, if you guys have seen Mike Brown's presentations. He used to work for VDOT, but now works for WJE. But this is one of his slides about how these cores or how these slices are extracted and tested. But we basically cut these cores. We cut out cores. Again, we prefer them over powder samples. We pulverize that concrete. There is a discussion about whether you use acid soluble or water soluble testing. I like acid soluble because that gets you everything, all the chlorides that are in that concrete. The challenge is, if you have bound chlorides within the aggregate particles, it also gets those because they're crushed, right? So generally speaking, acid soluble values are higher than water soluble values, and it just depends on the aggregates that you use about what that difference really looks like. There are these numbers are generally used to talk about corrosion thresholds, right? And there's a bunch of different thresholds because they depending on the bar type. There are also different ways that they're presented, right? So I've given you 3 for basically for black bar here, right? So VDOT uses pounds of chloride per cubic yard of concrete. You'll also see percent by weight of concrete, and you'll also see percent by weight of cement. Just be careful when you see these numbers. They do actually matter. And you can back between one and the other of them pretty easily, but that they can be confusing, at least for me. So we developed chloride. So we did the chloride testing, right? Took the cores, did the chloride testing. Here's the results of the deck, and I think the abutments. Decks on the left and abutments are on the right. Right. And what you see here is there's, relative to VDOT's limit, just as a simple, 2 to 2.5, right? We have very high chloride levels within an inch or 2 of the surface, right? And then lower levels past that for the deck. And then on the abutments, right, what you see is you kind of see abutment 1 and abutment 4 being very different, right? And this is likely due to exposure, right? This might have been underneath an expansion joint, and this was more protected because we did a couple different zones. But what we're doing here, at least for the deck, right, we would curve fit this data, right, potentially into one curve, which gives us like the mean and the standard deviation, so that we can use that as a normal distribution curve in the Monte Carlo approach of the service life modeling, right? We also do petrographic analysis, right? That's a common thing we do. What that gets you, right? What does that get you? It gets you carbonation depth. With carbonation depth, when it gets really deep, can produce corrosion and reinforcing steel, and carbonation plus chlorides can produce, kind of even higher corrosion rates. It'll tell you about the cementitious materials, of course, aggregates, fine aggregates. It'll tell you a little bit about paste to aggregate bond, water. We can estimate water to cement ratio. We can look at void characteristics, right? Void spacing and the amount of entrained or entrapped air. It also, in this area, we'll look for alkali ASR type degradation. I don't think, most of our structures won't see DEF. A lot of times that's associated with either mass concrete or precast type work that's been, cured at high temperatures, also freeze-thaw damage. So that's really, it may not necessarily go strictly into the service life model, but we often do it to get a better sense of what's going on. We did some compressive strength testing. Again, this does not go into the service life models, but it gives us an indication of what, kind of the range of quality of our concrete is that we're dealing with. So what did we do? Right. So the next step is we also, on this particular bridge, we did strain gauges and with a wireless data acquisition system to look at strains at the ends of the cover plates on the bottom right. This is the cover plate, so we're looking at cover plate termination stresses, right? And this is a little one of the cellular nodes that we used on this particular project. We got strain data. We did rain flow analysis, which is kind of separate from the service life modeling, but it's really talking about what's our fatigue life, right? And then we analyze data, right? So we're analyzing both the concrete data and the steel data for this particular project, right? So we have inputs that we need to put into the service life model, right? So if you look here in the distribution type, right, this tells you whether we considered it a constant or whether we consider it variable over time, right? And so the ones that are highlighted, right, those are basically normal distributions, right? Because you can see the standard deviation and the mean. So we did normal distributions for the chloride threshold, right? We did it for cover, we did it for the surface concentration, and we did it for the diffusion parent diffusion coefficient. So these two are back calculated from our chloride profiles. This guy is from our GPR work, right? And then the corrosion threshold, we've just done in-house research where we know we presented, we have these values kind of in-house. So all of that gets fed into our service life model, right? So this is what we end up with, right? We don't always use a lower bound and an upper bound. But in this case, we can just look at the model. So we look at the current damage, that's that black dot there, and then we're predicting when we see, let's say 20% surface damage, right? So we would say, hey, listen, we're at 45 years, at 55 years, if things stay generally the same, or 58 years, you're going to be in that 20% damage range. So now we can talk and maybe, if we say, listen, we have lower cover and higher diffusion coefficients, or higher cover and lower diffusion coefficients, it changes. But this is some kind of, consider it a mean type estimate. But what we're saying to them is, like, at 55 or 58 years, right, you're going to have a good bit of damage, and you're really going to have to be, considering replacement or significant renovation of that element. And this and you can do this in multiple areas. You can do this for multiple components. And what it does is, or what we find it does, is it allows the agency or the consultant to get a better handle on, hey, do we, how much do we really need to do? How fast is this going to progress? Can we push these decisions out 5 years? Do we not want to do that? And so it is probabilistic. So there is mechanisms, corrosion mechanism behind it. Again, a little off topic for this discussion, we did rainflow counting, and then we estimated fatigue lives based on AASHTO requirements. And ultimately, right, this structure, because it had very low traffic, fatigue just wasn't an issue on this structure. So then we produced recommendations, and in this case, we produced them in kind of, buckets of years, right? And I won't go into specifics, but they kind of range from like kind of maintenance-ish type repairs, right? With less than 10 years, repair spalls and delaminations, recoat steel, repair corroded areas. If you wanted to try to keep it, 20 to 30 years, here's what we think, right? You're going to start to see that 20% number pop up, right, of damage. Maybe you're talking about a more extensive overlay, right? Some kind of bonded overlay. You're going to be recoating the steel. If you want more than 30 years, then you're having to do some more, like, you're just going to have to replace the deck, right? And then do some other more intensive repair work. So this allows us to slot some of those recommendations in with backing from actual, analysis, rather than just kind of guessing at it. So to sum all this up, and I know this has gone relatively fast, to sum this up, this is what the bridge looked like. This is from VDOT's website, and I did talk to VDOT before this call. So VDOT did ultimately cut the piers off. They kept the abutments. They took off the steel, the old steel girders and the deck. And then on the right there, right, they replaced the abutments and the steel girders and the deck. So that's as of, I think, 2024 sometime. So I think the structure will be back in service early this. It was reopened. Sorry, it was reopened recently. So that was the outcome. And I think that may be our last slide. So, Michael, do you want to open it back up to the group? I don't know if we see anything in the chat.
Yeah, if anybody has any questions, please use the Q&A function here for Travis. Travis, thank you for a great presentation. I guess I'll open up the Q&A. question for, if you wanted to jump back to your recommendations, you had I guess it was like the 30-year light, or the more than 30 years. And when you do consider the cathodic protection, for these substructure units, how often, I guess, in your experience, do you see that, are they trying to, I guess, for, let's call it
Are you talking about right here,
mid-span.
right, Michael?
Yeah. So, for, middle span type bridges, how often do you see that? Because, obviously costs to do major rehabs or replacements for those, but when it comes to larger span, potentially historic, is that where you see more of this cathodic protection being used?
I think there's generally more attention paid in repair work, right? Because if you're doing repairs in chloride laden or carbonation, deep carbonated concrete, then I think anodes make sense because you don't get this ring halo effect, right? But on some of I think it's probably more common on more signature type structures. I'll give you an example. There's a structure down in Texas, called the Queen Isabella, and it was a model TxDOT bridge. They had done spray applied zinc on the pier caps that are in the water, right, of the intercoastal. And those pier caps look fantastic when they still had zinc on them. But we went back and looked at that bridge probably, very somewhat recently, which has probably been 15 years since we looked at it the first time. And once that zinc went away, those pile caps they went kind of down the tubes. And so I think it gets more attention on larger structures. I do think even just the discrete anodes is a pretty easy way to tamp down corrosion, because a lot of times we can't control moisture, right? We can't really control the chloride that's in the concrete to some level, right? And so I'm a proponent of it, and I like the spray applied zinc type application for certain instances, but I don't think it probably for like a standard bridge over like a roadway, like over a highway. I don't think you're not going to use it there probably, right?
Yeah. All right. Yeah, and if anybody has a question, I do have another one. I don't want to make it about me for Q&A.
Well, hopefully it
but
wasn't boring. Hopefully somebody will ask a question. Maybe Nate will make something up.
My next question was, when you're estimating, your service life and you have all that, do you have any calibration, I guess for environment, bridges, or structures close to, the coast, or, obviously, down south where they might not be using salts as much, for the winter. Is there a calibration in that sense, or is it just your built-in curves, will account that based on, what you're already seeing in your trends?
Yeah, we've done some validation studies. So part of it is, right, we'll use the example of a bridge down, let's say in Georgia, that where maybe they're not using chlorides, so their surface chloride level, and I'll jump back to those slides, right? Their surface chloride level will be low, right? And so, right, so in Georgia's case, let's say the cover is the same, right? The diffusion's the same, but the exposure is way low, right? Georgia may be really low. And so you're likely going to get in Georgia, and let's say the chloride threshold is the same for these two example bridges, one in Georgia and one in like New York, right? Well, this exposure is going to drive this curve. It's going to flatten that curve out, right? Whereas, in New York, if the exposure is very high, that curve is going to be much steeper, right?
Yeah.
And so it's kind of cooked into the math of it, right? But like all things, right? We do make slight modifications to how we process this data based on, our experience. And frankly, we've gone back to some of these structures and validated that we're even remotely close. But this methodology, just so you guys know, it's been around for a long time. This is not something that Janney just completely made up. I think what we bring to the table is we do a lot of inspection work, and we do a lot of NDE work, and we do a lot of, kind of repair work. And so we bring kind of the material side pretty strongly to the table with some of these existing modeling concepts.
Great, thank you.
Michael, to answer your question, I think exposure definitely is going to matter, right?
Yeah. I was just curious of, how much, I mean, obviously it plays a part, but what, just in terms of, you put a bridge in one location, it's obviously not going to have that same exposure at another location. And just how often do you see it, like you said, obviously it will affect a curve, it will flatten that out, but how by
a lot.
Is
I mean, it could be
yeah.
a lot. I mean, like, this modeling, right? If we talk about chloride modeling, this modeling doesn't really work in Phoenix, right? There's no chlorides. Now there's other modeling, there's carbonation, right? You can model carbonation, diffusion of carbonation, front and do something similar. There's ways that people look at all sorts of different deterioration mechanisms, but you're just never going to use this kind of methodology as in a structure in Arizona, or at least in the desert of Arizona.
Exactly. All right. Last chance if anybody has a question.
I feel like Nate has to ask a question.
Oh, here we go. All right, we have one in here from John. Was there concern about the replaced sections of the bridge being built atop the dam, that the remaining life of the bridge could be controlled by the life of the dam?
Of the dam. Yeah, for sure. For sure. I mean, we were fortunate in that case, right? That water supply, we tested the water, right? That water supply is potable, basically potable water. There's nothing in that water. That the freeze thaw damage was limited. Most of it was up top in the piers. And so in some senses, we were pretty lucky that we were able to salvage the dam. I think if we couldn't have salvaged the dam, whole different discussion. But yeah, eventually, right? I mean, the dam is a gravity dam, so well, to some degree, a gravity dam. So I think you're going to have many more years of service before that dam impacts the bridge. And the cost that VDOT paid to get what they have now for the 50 years that they're whatever they're looking for, that probably a pretty good deal.
Great. Well,
we're a little early.
Yeah, I don't see any more questions. Again, last chance. Oh, here we go. Are there failure mechanisms and predictions developed for ASR and ACR damage?
That's a good question. I don't think so. I'm happy to look into that. We're working on that down at the Marina Enon Bridge with BDI, but I don't think that there are, that's an expansive process, right? But I don't know that there are formal mechanisms for that, because generally what ends up happening with that is we decide there is or is not ASR occurring, mostly via paste and then, aggregate damage. But, there's lots of dams out there that have really bad ASR that perform just fine because they're, confined. So the short answer is I don't think there is, but I'm happy to look at it if you'd like me to dig into it more.
All right.
Well, I hope you guys enjoyed it. And if you have any questions, and if you want more details about service life modeling, just let us know, or let me know, or get with Mike, and we're happy to, help out any way we can.
Yes. All right. So I'll take over. So Travis, thank you very much for coming on, presenting. It was great. Looking forward to seeing if we have any more follow-up questions, get them back to you. But in the meantime, thank you again. And as a token of our appreciation, we will be sending out this nice SEI Philly Yeti mug for you.
Awesome. Thanks, guys. Appreciate it.
Yep. And then for your PDHs, for the attendees, you can click, or I mean, you can take a shot of the QR code. And if you check the Q&A chat, we will have a link up there in a second, and you can also go to that link.